Hello, I'm Rahul Baghel, Assistant Professor, Chhattisgarh Swami Vivekanand Technical University, Bhilai. Welcome you all to the course on Industrial Automation and Drive. Today, we begin with our 18th lecture on PLC Counter Programming Part 2. In the previous lectures, we cover up counters and their related examples. Today, we start with one-shot instruction in PLC programming. The one-shot instruction is also known as transitional contact, is critical tool in PLC programming that generate a brief output pulse lasting only for one program scan. This instruction is particularly useful in scenario where you need to reset counters or timers based on a momentary signal or a specific transition in input conditions. How one-shot instruction works. Under this, the first one is triggering the one-shot. The one-shot instruction is triggered by leading edge of input signal, meaning it activates when the input transition from an off state 0 to an on state 1. This transition is also known as the off to on transitions. Next one is duration. Once triggered, the one-shot output remains active for duration of one program. Next is scan. After that, it turns off regardless of whether the input signal remains on or not. Next is resetting. The one-shot stay off until the input signal goes off and then come back on again, at which point the one shot can be triggered again. Next one is use cases. Under this, resetting counters and timers. One of the most common application of the one shot instruction is automatically resetting counters and timers, since it is stay on for only 1 second. It ensures that the reset occurs only one per triggered event, preventing repeated resets during prolonged input signals. Next is momentary signals. If you have a momentary signals like push buttons, the one shot will trigger on the first press but will not trigger again until the button is released and pressed again. Next is persistent signals. If the signal stay on for a while, the one shot will still only triggered on the initial transition, preventing multiple outputs for a single input. Next is the types of transitional contacts. Under this, the first one is off to on transitional contacts, as you can see in the diagram also. This is most common type of one-shot instructions. It generates a one-shot pulse when the referenced input signal changes from off to on state. The contact closes for exactly one program scan and open even if the input signal remains on. This ensures that only one pulse is generated per input transitions, right? As you also see in the diagram, when my input is changes from on off to on, then only my signal is generated, right? Next one is on to off transitional contacts. This is also you can see in the diagram. It works similar to off to on contact, but it triggers on the trailing edge of the signal when the input changes from an on state to off state, that is 1 to 0. It provides logic continuity for a single scan when the input turns off, then opens afterwards. Next is benefit of one-shot instructions. Under this, the first benefit is precise control. By generating a pulse for only one scan, the one-shot instruction provides precise control over when action like reset or triggers occurs. This avoid multiple activation from a single input signal, which could otherwise cause error in the system. Next benefit is flexibility. One-shot instruction can be used with both momentary and persistent signal, making them highly versatile in various applications. Next benefit is prevent unintended repeats. By limiting the output to one scan, one shot prevent unintended repeated actions, ensuring that the processes only triggered once per input transition. To understand this one shot instructions, let's take some example. And under the one shot instructions, the three types of instructions will come. The first instruction is called ONS instruction, second instruction is called OSR instruction, and third instruction is called OSF instruction, right? So let's take example related to that instruction one by one. So here you can see in the first example is related to the ONS instruction. As you can see in the diagram, in the first rung, the switch is connected to the ONS bit, and the address of the ONS bit is provided by the binary input, that is B3 colon 0/0, and the address of the switch is represented by I colon 0/0 in the first rung. And the same you can see one binary output is also connected in the first rung, and the address of the binary output is represented by B3 colon 0/1. And you can see in the second rung the same binary output address is provided to the switch, which is connected in the input side in the second rung, you can see. And with the same switch in the second rung, my up counter is connected. The address of the counter is C5 colon 0, and the preset value for my up counter is represented by 5. And in the third rung, you can see my counter done bit is connected, and with this done bit, my output is connected, and the address of output is represented by O colon 0/0. And you can see in the diagram, the last rung is in the last rung, I'll provide another switch, and the address of that switch is I colon 0/1 is connected to the reset button or reset button for my counter, right? So let's take the first case. In the first case, when the input switch, that is I colon 0/0 is 0, means it remains their initial state, means it doesn't provide any changes. That's why the binary output doesn't get the supply, and it also becomes 0. And when the binary output becomes 0, my counter doesn't get any supply. That's why its accumulator also doesn't change from the initial value 0. That's why the done bit is also 0. That's why we didn't get any output, right? And let's take the second case. In the second case, when I press my switch, or my switch, that is I colon 0/0, changes their state from normally open to normally close, right? In these case, when I press my switch, my output, that is B3 colon 0/0, is on for a fraction of second, and because of that output, my binary output, that is B3 colon 0/1, is also getting on for fraction of second, right? I'm again repeating, when I press my input switch I colon 0/0, then my binary output, that is ONS bit, is on for a fraction of second. Because of that fraction of second, my binary output is also on, right? And to observe this binary output, my counter is also connected. That's why when my counter is get this binary output, this fraction of output, my counter is increased, its accumulator value is increased by 1, right? So I guess second case is clear to you. When I press my switch, my binary output get the supply, and when it's get the supply, my counter accumulator value just increases. There is start counting and increases their accumulator value by 1, right? And let's take the third case. When I repeat this process for the 5 times, after the 5 times, my counter accumulator value reaches to the 5, because my counter received 5 times outputs, and that's why after 5 times the done bit is high, and when the done bit is high, my output connected to the done bit is also high, right? In the third case, right, when I repeat the process 5 times, then my accumulator gets the supply for the 5 times. That's why the accumulator value is equals to the preset value, and in this case the done bit is high, and when the done bit is high, the output connected to the done bit is also high, right? That's why my output is high. So we can say that the ONS is an input instruction, and it's connected to the connected output to the ONS will be on for a fraction of second, right? Let's take the last case. In the last case, when I press my another switch, that is I colon 0/1, the reset button is on. If the reset is on, my accumulator value goes to 0 and my counter is reset, right? So I think this operation of ONS bit is clear to you. In the simple words, ONS bit will provide output for the fraction of second when it get the supply, right? Let's take example 2 related to the OSR bit. OSR represent one shot rise. As you can see in the diagram, one shot rise is connected to the output side, as you can see in the first rung, right? And you can see in the diagram the OSR bit takes two address, one for the storage bit and one for the output bit. The address of the storage bit is represented by B3 colon 0/0, and the output bit address is represented by B3 colon 0/1. As you can see in the first rung, the switch address is represented by I colon 0/0. In the second rung, I connect one switch with up counter, and the address of the switch is represented by B3 colon 0/1. The output bit of OSR, I'll provide the same address to the switch, right, as you can see in the diagram. And the counter address is represented by C5 colon 0 with the preset value of 5, and in the third rung I'll connect the done bit of the counter to my output, and the address of the output is represented by O colon 0/0. And in the last rung I use another switch and provide with the address of I colon 0/1, and this switch is connected to the reset button of my up counters. So let's take the first case. When the input is 0, when the input is 0, OSR bit doesn't get any supply. That's why the output bit of OSR, that is B3 colon 0/1, it doesn't changes their state, it remains in off state. That's why my up counter also doesn't get any supply. That's why its accumulator value is 0. That's why the done bit is also 0, and because of that output is also 0. So in the initial case, if input is 0, all the outputs are 0. In the next case, when I press my input switch, as you can see in the diagram, when the first switch changes their state, that is I colon 0/0 changes their state from normally open to normally close, my OSR bit gets the supply. That's why the output bit of OSR, that is B3 colon 0/1, also changes their state from normally open to normally close, but for a fraction of second. right? It also changes their state, but for the fraction of second. That's why you can see in the second rung the switch is represented by normally open, but you can see in the counter value the accumulator value is represented by 1. It changes because it's a fraction of second, it will change their state. That's why in the diagram you cannot see as a normally closed type. In the diagram it's represented by normally open only, right? So when I press my input switch, my OSR bit, the output bit of OSR get supply, and it will change the state, and it will changes the accumulator value from 0 to 1. And one more thing, it changes when switch status changes from off to on, means rise state. It changes, it provides the output when the status change from off to on conditions, means rise condition, initially rise condition, right? But in this case also you can see the done bit is 0 because my accumulator value is not equals to the preset value, because the preset value is 5 and accumulator value is 1. That's why done bit is 0. So the output connected to the done bit is also 0, right? And let's take the third case. When I repeat this process 5 times, means my OSR bit getting supply for the 5 times. That's why the output bit is also getting supply by the 5 times. That's why the counter getting supply by the 5 times. So my accumulator value increases from 0 to 5, and when the accumulator value is equals to the preset value, when the process is repeated 5 times, the done bit is high, and when the done bit is high, the output connected to the done bit is also high, right? So I guess you understand this process, right? And let's take the last case. When I press my last switch, that is I colon 0/1, the reset button get the supply. That's why you can see in the diagram the accumulator value again goes to 0, right? So OSR bit is represented by one shot rise, and it changes their state when state changes from off to on, that is rising condition, right? Let's take another example related to the OSF, that is one shot fall, and you can see in the diagram the one shot falling is also a output instruction. That's why it's connected to the right side of the rung, as you can see in the diagram also. And OSF bit is connected to the switch. The address of the switch is represented by again I colon 0/0, and you can see that the OSF bit is also taking two binary address, one for the storage bit and one for the output bit. So as similar to the OSR bit, I'm again providing the same address B3 colon 0/0, and the output bit address is also same B3 colon 0/1, right? And you can see in the second rung one switch is connected to the, again I'm using up counters, and the address of that switch is represented by the binary output of OSF bit, that is B3 colon 0/1, and the counter address is represented by C5 colon 0, and the preset value is 5. So when let's take the first case. When the input is 0, means input doesn't changes their state. That's why the one shot falling bit is also it also doesn't get any supply. That's why it also remain in its initial state 0. That's why the counter is also doesn't get supply in, and the accumulator value is 0, right? So the input is 0, all the output is in 0 state, right? Let's take the second case. When I press the input switch 1, my OSF bit gets the supply, and when the OSF bit getting supply, the output bit of OSF, that is B3 colon 0/1, gets the supply, and the accumulator increase by 1. In this case, you can also see the important thing is when the switch changes states from on to off, means falling state, then only the OSF will change their state, right? So in this case, when I press my input switch on to off, then my OSF get the supply, then it's provide the output bit, then the output bit address will also change their state from normally open to normally close, and the accumulator value increase by 0 to 1. But in this case also the preset value is not equals to the accumulator value, that's why the done bit is 0, that's why my output doesn't get any supply and it remains the off, right? Let's take the next case. In the case 3, when I repeat this process 5 times, my OSF receive uh, for the 5 times, that's why my counter receive the changes the input for the 5 times, that's why the accumulator value changes from 0 to 5, and after 5 times the accumulator value is equals to the preset value and it provides the done bit high, and that's why you can see the output connected to the done bit is also high. And you can see in the diagram the third rung, the C5 colon 0 slash done bit is high when the accumulator is equals to preset, that's why the output, that is 0 colon 0 O colon 0 slash 0 is also high, right? And let's take the last case. When I press my restart switch, that is I colon 0 slash 1, my accumulator value is reset to the 0, right? So in one shot instruction we have 3 instructions, that is ONS instructions, and second one is OSR instruction, and third one is OSF instructions. The first instruction is input instruction, that is ONS instruction is the input instructions, that's why it's connected to the input side, and the two instruction, that is OSR and OSF, are the output instruction, that's why it's connected to the output side. OSR changes their state when it's supply from one shot rise, means off to on, rising conditions. OSF changes their state when it gets supply from on to off, one shot falling, off on to off conditions, right? Let's take another example related to the compare instructions. Under the compare instructions, as you can see in the diagram, this is the actual view of RS logics. In the compare bit, we have lots of instructions. The instructions are LIM instructions, which represent the limit. MEQ instructions represent the masked comparison for equal instruction. Similarly, the EQU instructions represents the equals to instructions. NEQ represents the not equals to instructions. LES represent the less than equals to instructions. GRT represent the greater than instructions. LEQ represent less than or equal instructions. GEQ represent the greater than or equal instructions, right? So let's take another example related to the LIM instruction, that is limit instructions. As you can see in the diagram, in the first rung is connected to the I'm using the up counter with one switch. The address of the switch is represented by I colon 0 slash 0, and the counter address is represented by C5 colon 0, and the preset value is 20. The up counter preset value is 20. And in the second rung, you can see the LIM instruction is connected to the input side, right? So LIM instruction is an input instruction, that's why it's connected to the input side. In this case, you can see the LIM takes the 3 values. First one is lower value, lower limit, and the second one is higher limit, and the third value is the test. You can see in the diagram, I provide the lower limit as 5 and the higher limit is 10, and the test value is that is my accumulator, counter accumulator value. That's why you can see in the diagram the test address is C5 colon 0 dot ACC. It provides the accumulator value, right? And my limit in the second rung, the limit instruction is connected to the binary output, that is B3 colon 0 slash 0. And this in the third rung, this binary output is connected to my main output. The address of the main output is O colon 0 slash 0, right? So you can see when I press my input switch, that is I colon 0 slash 0, my up counter gets supply and its accumulator value changes by 1, right? But in this case, you can see my limit instruction doesn't provide the output, because my limit instruction provide outputs only and only when the accumulator value in between 5 to 10, because I provide the limit, the range is 5 to 10. When the accumulator value in this range in between 5 to 10, then only my limit instruction provides the output, right? So you can see in the next case, when I repeat this process more than 5 times or 5 times, you can see in the diagram the accumulator value is become 5. That's why you can see in the second rung the LIM instruction is provide the output. In the second rung, you can see my binary output B3 colon 0 slash 0 is high, and when it's get high, the output connected to the binary output is also high. You can see in the diagram that is O colon 0 slash 0 is also represented high, right? So I think you understand this instructions. Limit instruction means it limits it provides output for a particular limit, right? In this case, I set the range of 5 to 10, right? That's why when the counter value is the counter accumulator value is in between 5 to 10, then only it provides the output. Let's take another example related to the EQU instructions, that is equal instructions. In this case, as you can see in the diagram, I am using two counters. First counter is C5 colon 0 and the second counter is C5 colon 1, C5 colon 1, right? And the preset value of the first counter is 10 and the second counter is also using 10. As you can see in the diagram, the first counter is connected to the switch 1. The address of the switch 1 is I colon 0 slash 0, and the second counter is connected to the second switch, and the address of the second switch is I colon 0 slash 1. And in the third rung, you can see in the diagram, the EQU instruction is connected. So EQU is an input instruction, that's why it's connected to the input side. And you can see the EQU instruction also take two inputs as a source A and the source B. The address of the source A is provided by the accumulator value of the first counter, that is C5 colon 0 slash 0 dot ACC, and the address of the source B is provided to the address of the accumulator of the second counter. That's why it's C5 dot 1 dot accumulator, right? And you can see in the third rung the EQU is connected to the output, that is O colon 0 slash 0, right? And in the last two rungs, I'll provide another two switch to restart for my counters. Let's take the operation of EQU instructions. In the first case, when the both counters are in the initial state, means when I doesn't provide any input to the switches, the accumulator value is in 0. So in this case, you can see when the both accumulator is 0, that's why it's equal, because equal instructions compare when the source A and the source B is equals to 0. means the value of source A and the value of source B is equal, then only it provides the output. In this initial case, my both counter accumulator value is in 0 condition. That's why the source A value is 0 and the source B value is also 0. So both are same. That's why you can see in the diagram, the output is connected to the EQU instruction is getting the supply and it will become on, right? Let's take the another case when the both counter value is not equals. As you can see in the diagram, I'll changes the counter value by my switch 1 and switch 2. When the both accumulator value is not equals, in this case you can see in the diagram the first accumulator value is 3 and the second counter accumulator value is 1. So the source A is 3 and source B is 1. So this is not equals. That's why you can see in the diagram the output connected to the EQ instruction doesn't get any supply. That's why it is in off state, right? I think the EQ instruction is clear. EQE instruction provide output only and only when the source A is equals to the source B. Let's take another example related to the MEQ instruction, that is masked compare for equal instructions. As you can see in the diagram, it is also an input instruction. That's why it's connected to the input side, and one output is connected to the MEQ instruction, that is O:0/0. For this also I used two counters, that is C5:0 and the C5:1. In this case, you can see the source A, the first value to the compare. This is actual value in the memory that you want to compare against a reference value. And you can also see the MEQ instruction has, the second is the source B, the reference value to which the source A is compared, and the third one is masked. This define which bit are relevant for the comparison. Bit in the mask set to 1 are included in the comparison, while bits set to 0 are ignored. Means how it works, the MEQ instruction performs a bitwise AND operation between source A and the mask. It also performs a bitwise AND operation between source B and the mask. The result of the two operations are then compared. If the results are equal, then the MEQ instruction provides the output true. If the results are not equal, then MEQ instructions returns to the 0 or false, right? So that's all for the today's lectures. In this lecture we cover the one-shot instruction. Under this we cover the ONS instructions, OSR instruction and OSF instructions, and some compare instructions. The remaining compare instructions I'll cover in the next lecture, and in the next lecture we will also explore the counter programming. So thank you and happy learning.